Hello, and welcome to Chapter 6, Section 2, Part 3. This is actually your last video of the entire year. So this video, we're not quizzing on it or anything, it's just to help you with your project. So in this video, I'm going to show you about still volumes, but this time we're specifically looking at volumes where we have like this shape and instead of rotating, we're using a known cross-section. So what that means is, if you're dealing with a cross-section, that means like imagine you had some shape and you like cut through it. Whatever shape you end up with, that's the cross-section. So in the past, we've just been doing circles because volumes, after we rotate, when you cut through it, it makes a circle. So now we're dealing with cross-sections that are like squares, semicircles, triangles, different shapes. So you have some options. So that's what we're focusing on for your project as well. We're not doing circles because it'd be really hard to build something where the whole thing is round, because then it's just not as fun. So we're dealing with cross sections where your cross sections are like a square, a rectangle, semicircle, something like that. So here's my example. In this problem, we're looking at the area between f of x equals e to the x, so that's this curve right here, and then we're going to bound it using y equals negative 3, this line right here, x equals 0, and x equals 2. So we're just looking at this shaded region, but on top of this shaded region, instead of rotating it around anything, we're actually building squares on top, or sorry, semicircles, sorry, we're going to start with semicircles, on top of this shape. So our semicircles is going to be where our diameter is going to be vertical like this. So imagine like if I stuck a semicircle on top of this shape, like sticking out towards you, so that it goes over this shape. And let me give you a better visual of this. So here's my visual. So remember our green area was this part right here. So as we go through from left to right, we're basically looking at slices that look like this. So at x equals 0, there's going to be a semicircle that where the diameter of it goes from, it looks like 1 all the way down to negative 3, because that's like the length of that first green section of our shaded region. But we're going to build a semicircle on top of that. And then if I scoot over a little bit, then my diameter actually grows. So do you see how I'm going to make another semicircle, another one, another one, another one. But do you see the diameter? It keeps growing each time because it's going to match the length of from the curve to y equals negative 3. So as you keep going towards the right, that diameter keeps growing. So the area of each slice is actually changing every single time. So our goal is to find this total volume. So as you build all your semicircles all the way across, and then that's our last one, because that's where it ends at x equals 2. And so throughout that, when we set up our integral, that's when we're calculating the total volume of each of those slices added together. So for this particular problem, if I kind of just undo this really quick, then when we're talking about our volume, total volume here, we would need to set up our integral from 0 to 2. And then the equation inside the integral is going to be the area of the semicircle, because then the integral itself will add up all the semicircles for us. So area of a semicircle would be half times pi r squared, and then we would have to figure out what the radius is for each of our circles. So in this problem, the diameter for each semicircle is going to be that distance from like the top, the curve, to the line y equals negative 3. So our curve was e to the x. So if we do top minus bottom to find that distance, it would be e to the x minus negative 3. So that's the diameter for each semicircle, but in order to use our area formula, we would need the radius. So if I divide that by 2, that'll give me the radius of each semicircle. And then area then would be half times pi this squared. So really like this. And then that's what we're integrating from 0 to 2. So on your project, I'm not actually looking for you to actually integrate the whole thing. If you look through the steps, I'm just looking for you to set up the integral, because some of your shapes are going to be crazy. You might have multiple parts to it, so I'm not looking for like a final answer. The goal of our project is actually for you to build it where we're not doing like a bajillion different slices. Your minimum is going to have a minimum amount of slices, so each slice is actually going to be thicker than like doing a bajillion slices all at once. So when you do your slices, you're actually going to have a volume for each slice because there is a thickness to it. And then you're using that, you're going to calculate the volume of each slice, add them all together in order to estimate your total volume for your shape. Okay, so now that you've seen one problem and kind of like related this back to our project, let me show you another example. This time we're looking at the function 3x to the 1/3 power, so that's this curve right here. And then we're bounding it by the horizontal line y equals 6 and the y-axis. So we have this shaded area right here. So that's kind of like our base shape or our base graph that we're going to refer to in our project. So then for this one, we're going to use cross sections of a square. So we're basically looking at this length between y equals 6 and the curve to make a square on top of that length. So let's do the visual representation again. So here, right at x equals 0, we can build a square on top of this length right here, right at the beginning of our base shape. So that's going to be the biggest square because the length from y equals 6 all the way to the bottom of that curve is like all the way down here. So that's going to make a giant square right on top of it. And then if we make our next slice, then see how this one's kind of spaced apart. That's going to be similar for you. You're going to have some spacing between it. So this next length looks like they started like just past 0 right here. So now the length of the square is going to be a little bit less because this length is smaller. So, you know, a square, all the sides of the square have to be equal. So that's going to be a smaller square that you're building. And then find the area of that, keep going. Build another square. So as we go through across our entire base shape, the squares get smaller and smaller, but we're finding the area and the volume of each of those squares and adding it all together to find our total volume as we go all the way across. So in order to set up an integral for this, we would need to use the integral from 0 all the way to where this ends. It looks like it's at 8, and we could solve for that by setting our equation of 3x to the 1/3 equal to y equals 6, and that'll tell you where it intersects. So I think we would get x equals 8 for that, so we're integrating from 0 all the way to 8. And then the equation inside our integral is going to be the area of the square. So for each square, it would be, well, area of a square is just the side length squared. So our side length would be this distance right here from y equals 6 all the way to this curved part, which was 3x to the 1/3. So that means that length is going to be 6 minus 3x to the 1/3 since we're doing top minus bottom curve to give us the length. Okay, so the height of each square is still going to be the same. So the area would be that 6 minus 3x to the 1/3 squared. And then that would be the equation inside your integral from 0 to 8. Looking like that. And that's our setup. So that's all I have for this video. I just wanted you to get a visual for what we're doing with this project so that it's using cross sections instead of rotations. But really the ease of calculating things should be easier because we're not rotating, and building a project like this should be easier. Alrighty, that ends our last video of the year. Thanks for watching. Don't forget to like and subscribe. Bye!